Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we'll be starting the lecture 8 of Bode plots. So, previous lectures we studied about the steady state error, about like what does initial slope means, and like different coefficients. Even though I told you that you don't need to remember, but sometimes it helps you to remember, or sometimes they directly ask the question from this coefficient, error coefficient itself. Like, can you find me the acceleration error coefficient of this block diagram, or from the Bode plot? So then obviously you have to remember the definition also. Okay, so that is the main thing. And before that we studied about this like how to find the phase margin, how to find the gain margin from the Bode plot. Pretty simple, not that difficult. Okay, and like the what about the errors? What are the errors in the magnitude of the corner frequency? And for phase, the error is 0. So these three things, simple topics we learned. Okay, small topics we covered. So in this lecture, what we will cover? We'll basically cover the Bode plots for standard second order system. Now you might say, sir, but we have already done second order system for Bode plots. Again, why we are doing it again? Now the difference is, until now, whatever second order system we are plotting the Bode plot for, like let me take one example in of whatever second order system we are plotting something like this: s tau 1 plus 1, s tau 2 plus 1. Okay, so these we are plotting. Okay, now if these we are plotting, now these are what? These are real and unequal roots, or they may be equal also, but they are real roots. They are real roots. Okay, they are real roots. But now let's say if you have an underdamped system, now what happens in an underdamped system? Your roots are complex conjugate on the left hand side, but complex conjugate. Now how will you plot the Bode plot for those type of systems? Because their roots aren't real, so you won't be able to express them in the x-axis, in the omega axis, because roots aren't real. That's why, like, what was the expression in the omega? Like, what were the poles here? The poles were the s equals to 1 by tau 1, s equals to 1 by tau 2. Like the poles were the locations here, right? Corner locations, corner frequency locations. But now we won't be able to do that. Now our corner frequency will change, many things will change. So we have to make few approximations for plotting the Bode plots of second order standard second order system. For mainly, this lecture is mainly for underdamped systems. Underdamped systems, because there the concept of zeta comes up. Okay, underdamped systems. Okay, so before that, obviously I gave you a homework, so we have to complete that obviously. So this was the homework. I hope you have done it. What you have to do is, the Bode asymptotic magnitude plot of a minimum phase system is shown. A minimum phase system is shown, and if the system is a unity negative feedback, everything is good. The steady state error of the closed loop system to a unit ramp input. So what will be the steady state error for a unit ramp input? Now just remember one thing, like they have given you unit negative feedback system, and this is the like OLTF. Okay, so they have given a G of j. They haven't told this is OLTF, but you understand this, right? This is the OLTF. So from the initial slope itself, you understand that it has a minus 20 dB per decade initial slope. So obviously type is 1. Obviously for unit ramp input, you'll get finite error. Like these things, you have already like known all these things with good practice. So first observations from the Bode plots. Initial slope equals to minus 20 dB per decade. Okay, initial slope equals to minus 20 dB per decade. So this is the first order. So my order, like type will be 1, type 1 system. Type 1 system. 1 pole at the origin. Next, what we observe is, then after here, my slope is like here. My slope was minus 20 dB per decade. Okay, let me mark over this only. Slope was minus 20 dB per decade. Now here it became 0 dB per decade. That means my slope got increased. That means I have a 0 at this location, and slope got increased by 20 dB per decade. That means I have a 0 at this location. Okay, like 1 0 at this location, 1 0 at this location. So at omega equals to, not here, yeah, at omega equals to 2 I have 1 0. So corner frequency omega z1 equals to 2. Okay, 1 0. This is in radian per second. Then at 10 my slope is again going from 0 dB to minus 20 dB per decade. Okay, so here, like at omega equals 10 I have another corner frequency, and it is a pole, single pole, because from 0 it is going to minus 20 dB per decade. Just hold on, let me check if everything is recording. Yeah, everything is recording. So I have a pole, like second pole, at 10 radian per second. Now what will my OLTF look like? G of j omega or G of s. G of s will look like k, like some value k, into s. I'm writing in simple time constant format, by s by 10 plus 1, and we have also a s. Now how will we understand the value of k? How will we get the value of k? Like what we have to do is we have to find the steady state error. For finding the steady state error, like either you can use that formula of velocity error coefficient, or you can use the simple basics. Basics we'll do. From basics, first we'll do with basics, then we'll use the velocity error coefficient. So here, if you observe that at point 1 my magnitude in dBs is 26.02. so like this is at s equals to 0.1. so g of j omega at omega equals to 0.1 is equals to 26.02 dB. Okay, so now what is it? So here this is equals to 20 log base 10 magnitude of g of j omega equals to 26.02. so this is equals to 10 raised to power 1.3. Now if you remember correctly, like what can I write as 10 raised to power 1.3 if you don't want to do it in the calculator? If you don't want to do it in the calculator itself, like obviously if you are uncomfortable, then obviously you do it in the calculator, but if you can skip the step also. What you do is, it is 10 raised to power 1 times 10 raised to power 0.3. Now if you recall correctly, this 10 raised to power 0.3 is 2. This we have to remember, 10 raised to power 0.3 is 2, 10 raised to power 0.6 is 4. Okay, because it's simply the square. So this is equals to 20. G of omega. Okay, so yeah, this is the in absolute, not 20, yeah, this is 20 in absolute values. Okay, G of omega is 20. Now what is the value of k? What is the value of k? So for k, like magnitude of g of j omega equals to, like what expression can we write? This is k by omega itself, because we are simply approximating it, because if you put the magnitude, this 0.1 by 2 whole square will vanish, 1 will remain. The 0.1 by 10 whole square will vanish again, this 1 will only remain. So we are remain with k by omega itself. So k by omega equals to, like this is at omega equals to 0.1 equals to 20. So k equals to 2 simply. So my value of k is 2. Okay, so I can write here that my g of s equals to 2 by s by 2 divided by s into s by 10 plus 1. Okay, so this is what my g of S is. Now what else? Now obviously what is the steady state error formula? Like if you remember from the block diagram, I'm not drawing the block diagram, we remember, right? For a negative unity feedback system, it is very simple. The steady state error was simply this: S limit S tends to 0, E of S equals to S into R of S minus C of S. Okay, C of S is the output. Now if we take common R of S, here also we have limit S tends to 0. So what does this become? So this becomes simply this limit S tends to 0, S into R of S into 1 minus what? G upon 1 plus GS, G upon 1 plus GS. Now this, like I'm writing this again and again, deriving this again and again, because I want to show you that you can do it from basic stuff. You don't have to remember anything, but you can do it directly also. That's your choice totally. So S R of S, this is 1 by 1 plus G of S. Okay, now what is happening here? Now let's put the values. So simply, what is R of S? R of S is unit RAM, so it is 1 by S square. Now this is what is like 1 upon 1 plus G of S. What is G of S? G of S is K by not K, 2 by S into S by 2 plus 1 divided by S by 10 plus 1. Okay, so now what you do is simply we have an extra 1 by S term here, we can multiply this over here, right? So this limit S tends to 0, like this 1 S gets cancelled, still I have 1 S over here, so this is S, so this is S plus this S gets cancelled, and here I can put 0 simply, 0 plus 1 by 0 plus 1. Okay, and again I can simply put 0 over here, no issues. So this will be like my E of t. This is what my E of t, right? ESS of t. ESS, steady state error, 1 by 2, which is equals to 0.5. So obviously it will not take you that much time. You can do it easily also. Like also one thing I forgot to mention, you can also find the value of K in just seconds also. Don't need to do all this magnitude calculation. Okay, like gate gate has given you option. What you could have done is, like you could have either done this one, or what you could have done is directly. So this is like method 1, and method 2 is, method 2, like it is basically the shortcut, which is K equals to omega GC. Okay, basically it is like one pole at the origin, that's why the intersection at the 0 dB axis will be equals to omega GC will be equals to K raised to power 1 by n is 1, so K equals to omega GC, unity gain frequency, so it is 2 itself, K equals to 2 itself. Like directly from the graph itself you can understand that K will be equals to 2 without even doing anything. So this is another method for solving, like finding the value of K. Now here this was the method for finding the value of steady state error. Another method, what is another method? Simply the velocity error coefficient. So velocity error coefficient, okay, so velocity error coefficient. So now, like what is kv? Kv is equals to K itself, we know this. Okay, like kv equals to limit S tends to 0, S g of s, which is equals to k itself, which is equals to 2, and my E steady state will be equals to 1 by kV, which is equals to 1 by 2, which is equals to 0.5. Okay, like yeah, this will take you seconds, but obviously if you don't want to remember things, if you want to solve from basics, you can do this, because someday they may ask from basics, so then you will be stuck. Okay, so that is the thing. Just remember that this kV is applicable for type 1 system and for a unit ramp input. Like the ramp magnitude may be anything, not unit, like 5 times unit ramp, 6 times unit ramp, that doesn't matter. Here a will extra come. Okay, that is fine, but yeah, that is more important. Okay, so yeah, that is it for this question. Let's go to the topic of this lecture, basically Bode plots for standard second order system. So basically this is a standard block diagram of a standard second order system. We already know this. This is the OLTF of a standard second order system. Here my type is 1, order is 2. Okay, type is 1, order is 2. So what can we deduce from this one? So we can deduce that my, like, about the Bode plot, as my type is 1, my initial slope will be minus 20 dB per decade. Initial slope will be minus 20 dB per decade. Okay, and what will my initial phase? Initial phase will be minus 90. It will not start from 0, because type 1, right, s equals 0, you put this one will contribute to 0 degree angles, but this one always contributes to minus 90, always. So initial phase will be minus 90, and what will be my ending slope? As order is 2, now as order is 2, ending slope will be n minus m into minus 20. So here m is 0, number of zeros is 0, n is 2. Okay, so 2 minus 0 is into minus 20, so it is minus 40. So ending slope okay, so this is my ending slope. Now, like, what are the Bode plot of standard second order system? Let's draw. Basically this is like mainly what we'll do is for zeta based system. Okay, zeta is between 0 to 1. So like, what is my CLTF here? Like, this is my OLTF. What is my CLTF? And for CLTF we're plotting. For CLTF we're plotting the transfer function, because for this though, this is simple. This is simple. Like, their poles are like are not equal, and like they are real also. Here, but we want to plot for complex conjugate poles. That is the important. That is the motto of this main lecture. So my CLTF simply T of s equals to k omega n square divided by s square plus 2 zeta omega n s plus omega n square. So this is my CLTF. Okay, now this is the frequency response. Okay, don't get confused, like we were doing for time domain response, right? Remember, we are doing for time domain parameters varying the zeta and all those things. So don't get confused with the frequency response and the time domain response, because we have done the frequency response also. Okay, the graphs will come like the peak resonant, we'll quickly devise peak resonant, like the resonant frequency and the bandwidth, all those things. Okay, so like this is the in s terms. Now we will write this in like omega, in terms of omega. Like we want the frequency response, right? We want the frequency response, hence we'll put s equals to j omega. Now if we take equals j omega, what do we get? This is k omega n square divided by minus omega square, because minus like j omega whole square is minus omega square, because j square is minus 1, plus 2 zeta omega n j omega plus omega n square. Okay, so this is my value. Now what I will do is, I will do one thing, that as I want to compare my omega, right, I want to vary my omega between low frequency and high frequency region. Here it is not very easy for me to compare my omega with something. So what I will do, I will divide by omega n square on both numerator and denominator, so that I can compare my omega with some ratio, right? So as I want to approximate for low frequency region and high frequency region. So here dividing both sides, like this is t of j omega equals to k divided by, now this is what, like if I divide by omega n square, this one will become 1 minus omega by omega n square. So 1 minus omega by omega n square. Okay, then plus this is 2 zeta omega into omega n. So this is like, well, omega n is like omega n square is getting divided, so this omega n will get cancelled and another omega n will remain. So we'll get 2 j will be in front, 2 zeta omega by omega. Now we can simply compare our omega with omega n. So what we can do, we can compare for the high frequency region and the low frequency region. So what will my magnitude of t of j omega? K under root 1 minus omega by omega n whole square. Okay, and this is whole square again, plus 2 zeta omega by omega n whole square. And what about my phase? Even though we'll not draw the phase plot, because like it will be not that difficult, but still we won't draw it. I'll try. I will see if we get enough time. So now what about the phase approximation? So like what about the phase expression? So the phase expression is t angle of t of j omega equals to minus tan inverse, as we have pole, right? Like this is the denominator, that's why we get negative tan inverse. Now this is very negative. This is very important, that like if this term is varying, like omega and omega n both are positive, that is omega and omega n both will be positive. But if omega and omega n both are positive, but if this term is more than 1, then this real part of the denominator becomes negative. Real part becomes negative. That means in which quadrant I'm lying on the this second quadrant. So what will my angle here? My angle will be 180 minus theta instead of simple theta. If this was positive, like if this omega n is less than 1, so this whole real thing will be greater than 1. What does that mean? That means I'm lying on the first quadrant, so my angle will be tan inverse theta. So do remember that. So we'll just write the conditions in the next page. So basically to like the imaginary upon the real, 2 zeta omega by omega n by 1 minus omega by omega n whole square. Now when will this be applicable? This I have to like take the mod of this one. Take the mod of this one. As omega by omega n is positive, but this 1 minus omega by omega n square may be negative. That's why we'll take the mod of this one. And when will this condition be applicable? When will this formula be applicable? When when omega by omega n is less than, okay, then only this will be applicable. Just take a note of that, and it will be equals to tan inverse 2 zeta omega by omega n, and obviously we'll have a I forgot, right, minus 180 also. Like this term, what will happen, it will be theta 180 minus theta, and it is in the denominator, so 180 will come above, so minus 180 plus theta, minus sign will get multiplied, so this time it will be minus 180 plus theta. So it is simply again mod of okay. So when is this condition valid? This condition is valid when my omega by omega n is greater than 1. When my omega by omega n is greater than 1. So yeah, these are the two angle values and the magnitude values. Now let's approximate our Bode plot, like approximations. What is the approximation? Basically, when we are approximating for the low frequency region, and in the low frequency region, what is happening? When my omega is much less than omega n. Okay, omega is much less than omega n. So this is the low frequency region. So here what is happening to magnitude? Omega is much less than omega, and that means my omega by omega n is much less than 1. This is one thing. So omega by omega n is much less than 1. What does this mean? What happens to the magnitude if omega by omega n is much less than 1? So 1 minus this whole square, this can be ignored, so I am only left with 1. So 1, and this is also much less than 1. Zeta is between 0 to 1 itself. Zeta is between 0 to 1. Okay, so if zeta is 0 to 1 and this is also much less than 1, so this and if we square this one, so let's say 1 into 0.1, 0.1 whole square 0.001, 0.01, it is even lesser than this 1 itself, so I'll be only left with 1. So I can write now here, as I have k, it will be k. This one will tend to 0, this one will tend to 0. Okay, so obviously this will be k by 1 itself. This will be k only. Okay, in dBs, what will be the magnitude in dBs? Let me write it in different page. In dBs it will be 20 log base 10 k. Okay, so in dBs it will be this. Now if k is 1, now this is the approximation, just do note this is the approximation, we are approximating it. It will be equals to 0 dBs. Okay, so this is the approximation. Now what about my phase angle? So phase angle, if you observe, what formula we will use? We'll use this one, because obviously my omega is much less than omega n. So if we'll use this one, then what do I see? Like this is, again we can ignore this one, this is 1, and this is also very low value. So this is going to 0. So tan inverse 0 is almost 0. So this will be also approximated to 0 itself. Now don't get confused, at the starting of the lecture that was for the OLTF. This was for the OLTF. Okay, this was for the OLTF, not for the CLTF. Now for the CLTF I'm talking here. So the angle will start from 0. Now let's talk about the high frequency region. Okay, let's talk about the high frequency region. So in the high frequency region, what is the condition? My omega will be much greater than omega n. So my omega is much greater than omega n. So what does this mean? This means basically mathematically this is omega by omega n much greater than 1. Okay, omega by omega n is much greater than 1. Just let me put the mic more closer. Yeah. So what is happening to my magnitude? So basically, if my omega by omega n is much greater than 1, what will happen? This will dominate, right? So like it is much greater than 1, so on 1 is lower than this will dominate, and yeah, this will also be present over here, but this will more dominate. So we'll see. So let me first write the expression. Obviously what will happen is k will be at the numerator. Obviously we're left with 1 will get ignored, and this omega by omega n whole square, and taking the whole square again, plus 2 zeta omega by omega n whole square. Okay, so this one becomes k by, now this one becomes power to the like omega by omega n to the power 4. So let's like write omega by omega n as x. X is very high, x is greater than 1, very high. Now we have x to the power 4 plus 2 into something 0.1 or like something 0.5 zeta, like something like into x square. Okay, or like this is 4 zeta square x square. Now let me name this omega by omega n as 10. So this is omega 10 to the power 4, and this is what at max how much can it reach? 2 into 10 to the power 2. Okay, this 10 to the power 4 and this 2 into 10 to the power 4. So this is again very like low value in terms of this. Okay, this has high weightage. Okay, this has very low weightage. So obviously I'm approximating it, so I will choose this one and I will ignore this one. Okay, ignore this one. So finally I will get omega by omega n whole square, as there is a under root also at the outside. So finally my magnitude T of j omega equals to into k, omega n by omega square into k. Okay, So, and like what is the value in dBs? So in dBs is where we'll understand the main thing. So this is the value in absolute scale, decimal scale. So let's understand dBs. So it is 20 log k, and omega n square is a constant. So I'm writing the constant by themselves. Okay, writing the constant by themselves, and I will write the other terms in other manner. So this is minus the omega is varying, right? So I will write, I'm writing it separately. So this is omega square. Now further I can rewrite this one, 20 log. Now if k is equals to 1, okay, okay. So here, like what we observe, like the whatever term in front of this log based in omega, what is this? This is the x-axis, right? And this is the slope of the x-axis. Basically, this is the slope of the graph. So minus 40 is the slope. So here slope is dV per decade. Okay, slope is minus 40 dB per decade. So my slope is this. Now what's next? Like what is the phase? What is the phase? So phase for this one, T of j omega. Now what expression we will use? We'll use this one, because my omega by omega is much greater than 1. So if we will use this one, this expression, then what happens here? Basically, this is much greater than 1. Okay, hence like this one will be much like let me just write, copy this one. Just copy this one. So what is happening over here is, like we can approximate this, because this is much higher than this one, so we can write only this. Okay, because one is getting ignored and there is a mod sign, so negative sign also goes away. Now by obviously the square is positive. Now this one will get cancelled, so obviously I can delete this one. Now this is 2 zeta, which is already very less value, and omega by omega n is very high, very high, and this is less. So obviously this whole thing will tend to 0 degrees. So obviously my angle this time, it won't be 0, it will tend to minus 180, and that is understandable, because at high frequency order is 2 obviously. So my my phase will end at minus 180, and my order is 2, so my slope will end at minus 40 dB per decade. But what is the difference here? Like you might say, sir, we did this already, we already know all this, why are you saying this again, over and again? So we'll understand that. So here my angle of T of omega equals to minus 180 degree. Okay, so this is my angle in approximation, basically. Okay, in approximation. So this is my angle. Now like what is the difference here? So the difference here is that we are not taking into consideration about zeta. If you notice carefully, how much, whatever zeta may be 0.2, zeta may be 0.3, whatever zeta may be, we are not taking into account, because zeta is getting ignored. So I will write that in both, we slowly understand this, slowly you go through the lecture and you will understand the full concept. In both high frequency and low frequency region, low frequency approximation, we are basically we are basically we are ignoring the zeta. Okay, the zeta is getting neglected. Zeta is getting neglected. Okay, so zeta is getting neglected. So here, like, I've written the summary. Okay, what happens, like, at low frequency region and high frequency region, and this part will come to okay, so here, like, from here we can understand that the slope is minus 40 dB per decade. Now what is the interesting fact here is that what is the corner frequency? You said that our roots will be complex conjugate, like if zeta is between 0 to 1, our roots will be complex conjugate. So if our roots are complex conjugate, then what will be the corner frequency? So if you remember correctly, the corner frequency, like for Bode plot, the corner frequency are defined in two ways. So one of the ways was that wherever my two asymptotes meet. So corner frequency, like if you recall the definition, where my asymptotes meet. Okay, so this is the definition of corner frequency. So here, like, where are my asymptotes meeting? So if you look carefully, like if omega is much less than omega n, it is 0, and if omega is much greater than omega n, it is minus 40. So obviously they will meet at omega n itself. So at omega n, I will have a corner frequency. Because omega n is the limiting condition here. Basically, it is the approximating condition that with what we are approximating it. So omega is greater than omega n, it is minus 40 dB per decade. Omega is less than omega n, it is 0 dB per decade. So omega n will be my corner frequency here. But are these the poles? Like, tell me, are these the poles? No, the complex conjugate poles lie somewhere else, obviously, and we can plot it in the dB like x-axis. But we have to do some approximation. We want to plot the Bode plot for the this standard second order unadam system. We want to plot it, like that is the need of the hour. So for plotting that, we are doing some approximations, and what are the trade-offs of those approximations, we'll understand slowly. So unadam system is omega n. So the corner frequency for unadam system is omega n. Okay, so this is the corner frequency. Now basically, let's do one thing. Let's recall few things about the frequency response of second order system. So if you recall, for an undamped system where my zeta was 0, how was my frequency response? What was happening? Like, resonant peak was increasing as my zeta was reducing. Resonant peak was increasing. So at zeta equals 0, it went to infinity. It blew up. So this was the response. Now can we plot the Bode plot for this one? So generally we don't plot the Bode plot for this one, but if we really want to plot the Bode plot, then what we do is do a very high approximation. Like if in the examination, in some examination comes up, like in some other examination than gate, okay, it may come up. So here, what will be my T of j omega for this undamped system? T of j omega will be this k omega n square. Zeta is 0 this time, so this is minus omega square and plus omega n square. Like you can write the T of s also. omega n square. Okay, so this is what my T of S is. Like you replace S equals to j omega frequency response, you get this. Now again the low frequency region and high frequency region. So low frequency region. So let me just write like here, like we don't even have any imaginary term. This is totally real. Okay, for low frequency region, what is happening? For low frequency region, this omega will be much less than omega n. Now if omega is much less than omega n, then obviously this one will get, we can ignore, and this will be omega n square by omega n square. So we will remain with only k. So we will be only remain with k. T of j omega equals to k, and in dB it is 20 log k. Okay, I can, yeah, 20 log k. In dBs. Okay, so it is 20 log k in dBs. Now what about the angle? Angle, like this is positive only, right? Only k is present. So like T of j omega you can write, yeah, T of j omega you can, this is approximate actually. Okay, so this is positive, only phase is positive, so obviously it will be 0 degrees. It will be 0 degrees. Okay, so phase will be 0. The k is greater than 0, right? K is greater than 0, that is already we know, that is initial condition. So k is greater than 0, so this is 0 degrees. Now what about my high frequency region? What is happening to my high frequency region? So high frequency region, basically this what does my T of j omega become? So T of j omega, obviously here my omega is much greater than omega n. So my omega is much greater than omega n. What does this mean? My T of j omega will be equals to simply this k by omega n square will remain, but obviously now we can ignore this because omega square is much higher than this. Okay, so we can ignore this. So let's assume few numbers. Omega n is 1 and omega n square is 10, or you can say 20. So it is minus 400 plus 1, doesn't even matter. So this will be minus omega square. So now things change a bit. So obviously this is minus k into omega n, like this omega n square into 1 by omega square. Obviously these are positive, but there is a negative sign over here, so phase obviously changes. That is the first thing. But what about the magnitude? As there is a negative sign, we can, like, while we're taking the magnitude, the negative sign will go away. So magnitude equals to by omega square. Okay, this is the magnitude. Now in dB scale, 20 log k omega n square, this is constant, minus 40 log omega, like this 2 I have taken outside. Okay, power 2 I am taken outside, so this is minus 40 log omega. Okay, so here, from here we can understand the slope is minus 40 dB per decade. But at corner frequency, what is happening? Now if you put omega equals to omega n here, this blows up. Omega equals to omega n, this blows up. So omega equals to omega n, this blows up. So obviously, like in dB scale, what will happen? Log of infinity is infinity. So in dB scale, if you really want to plot it, so it will blow up. We'll show it like obviously my omega r is not omega n because like it is infinity, like the magnitude is infinity. Okay, so obviously it blows up. And like, what is the phase? Can you tell me the phase? Like if you calculate the phase, you can write in the comment section that it will be what? It will be simply 90 degrees. It will be 90 degrees. Okay, so am I correct? If omega equals to omega n, what? No, sorry. No, we can comment like phase just abruptly changes there. So yeah, we shouldn't comment over the phase there. So like here, like we can name this resonant peak or resonant frequency, or we can just write this as omega n. Okay, corner frequency is omega. Now what is happening here? Initially it is constant, even though I am not showing it as constant. Initially it is constant, but how can I show it? So what Bode approximation is telling us is that it will be something like this. Okay, it will be constant and then it suddenly blows up and then goes down. Okay, so there is huge error. Okay, obviously it is infinity. Error is not even defined for this one. Okay, error is not even defined for this one, but still. So if you want to quantify it like that in dBs, like few government examination, this question may come up by rare chance. Okay, minus 20 dB, minus 40 dB per decade. Okay, and this is 0 dB per decade. Okay, so this is the case basically. So now, like, this is for the undamped case. Now let's go for the underdamped case. So for the underdamped case, if you recall few things, like this was the plot when my zeta was varying from 0 to 1. Obviously here one thing, okay, not from 0 to, actually one thing, zeta, like we got a peak resonant, okay, when my zeta was I didn't even copy that. So I will do one thing, I will plot another thing. So here, right, so my zeta is not, like, for the Euler curve my zeta is varying from 1 to under root 2. Okay, and for the green curve my zeta is varying from 1. Okay, so obviously if you remember it, so like we won't used to get like any resonant peak when my zeta was greater than 1 by root 2 or 0.707. So green curve represents this and yellow curve represents, both are underdamped system, but the resonant peak we get when my zeta is between this range, and when zeta is outside this range, my, like, the DC value is the highest value. Okay, so that is about this, and the bandwidth is defined like this. Why is bandwidth defined like this? Because this resonant peak keeps on changing. Okay, that's why we define our bandwidth with respect to this closed loop, like the decision. Okay, so we'll write like one point, I forgot to write that point over there at that point of time. So bandwidth is up to the designer. Okay, so definition of bandwidth is up to the designer. Okay, now here like generally it is defined with the respect to the peak itself, but here as my resonant peak varies with zeta, hence we define bandwidth with respect to DC KCL as it is not changing, okay, as it is not changing. So this is one thing. So yeah, this is about this underdamped system. So now like, let's draw the Bode plot for this. So we have already done this, right? We have already done this. So here we lose our information about zeta. So this is for zeta between 0 to 1. So we can't tell about resonant peak or something. Okay, so we lose information about zeta. Why do we lose? Because we wanted to plot the Bode plot, and like for complex conjugate roots. So for complex conjugate roots we won't be able to plot, because what we have been doing until now was plotting for real distinct roots or real repeated roots. Okay, but for complex conjugate roots, how will you plot it here? How will you plot at omega? Okay, like omega is what? S equals j omega, simply. Okay, S equals j omega, and when this was real, then only we would have plotted here, right? But now what we're doing is we have a complex part of this S also. So it is not able, we are not able to plot it here in this axis. For all those things, we had to approximate the plot to do one thing, that plot the standard second order system here. Okay, so for this case, what would my corner frequency here, right? As I shown it, the like at high frequency region, the asymptote is minus 40 dB per decade, and here it is 0 dB per decade. So like they are meeting here, these two asymptotes are meeting here, and this meet point is known as corner frequency, which is equals to omega n. Which is equals to omega n. And this DC value 20 log k. Okay, this value is 20 log k. So this is basically the plot for this Bode plot for this zeta based system. Now let's understand what are the ramifications for this. Basically, what are the drawbacks we have to get, like for plotting this, because there will be some drawbacks because all the information of zeta is lost. So what is the, like if you just blindly see, before studying this lecture, right, blindly see this graph, what do you say? You will say I have two real poles at omega s equals to omega n. Okay, two real poles at s equals to omega n. But is it really? No. This is a zeta based system. So obviously we have lost our information. So obviously we are making some error. We are making some error here. So what is the error we are making? So let me first write the actual expression of T of j omega. T of j omega was k. Let me write it like this. I'm writing it with the normalized thing. So it is omega by omega n square plus j 2 zeta omega by omega n. This was it. Now let's do one thing again. Write the magnitude expression. So the magnitude expression is already written. So like let me take the magnitude expression of the dB in dB scale. So in dB scale, where is it? It's here, right? Okay, I have to write it directly now. Like I want to write the exact magnitude expression for this exact magnitude expression. So in dBs I want to write so that I can find the error. So like obviously you understand that at omega n we will make the maximum error, because here no magnitude is changing, but in actual reality what is happening, as my omega is increasing, the magnitude is reducing. Okay, magnitude is reducing, or it can increase also. It can increase also depending on the value of zeta. If zeta is less than 0.707, what will happen? I will get a resonant peak, so it will be like this. Okay, magnitude increase. Or if zeta is more than 0.707, then it will reduce. So obviously it will change. Okay, it will change, and at here we will get the maximum error. So let me write this in let me write the magnitude of j omega at omega equals to omega n. It will be k, and if I put omega equals to omega n, this one vanishes. Like this is omega by omega n, which is 1 itself. So this one vanishes, and this is omega n by omega n 1. So we are left with only 2 zeta, j2 zeta. The magnitude will be k by 2 zeta. So in dBs, what it will be? log 2 zeta. So in dBs, this is my magnitude. So this is in dBs. Okay. So basically now what is happening? Now we have to find the error. So like what is the actual value? Like what is the approximated value? So this is the actual, and what is the approximated value? It is what? It is 20 log k, but here it is still 20 log k. So this will be 20 log k. Okay, so this will be 20 log k. Now what is happening? What is my error? Error was actual minus approximate value. So actual was 20 log k minus 20 log 2 zeta, approximate 20 log k. So what is the error we are getting? The error in dBs is minus 20 log 2 zeta. So this is the error we get. Now just for context, put few values. Put zeta equals to 0.5. If you put zeta equals to 0.5, what do you see? This becomes log of 1, so the error becomes 0. Fine. Now if you put zeta equals to 0.9, or let's say if you put zeta equals to 0.1, this one becomes 0.02, and log of something negative is here, and the negative sign will come up here, and it will be 20 times almost 2 by 10, and it will be very high. It will be very high. If you calculate it, it will be very high. So yeah, if you see, the error is varying, okay, and it can be, it depends on zeta, obviously. So because we are neglecting the information of zeta, so zeta will come somewhere, right? So here zeta comes, the error comes with, it comes with error because we are neglecting the information of zeta. That's why. So this formula, this error formula is only valid for zeta based system, second order unadam system. Okay, to remember this, second order okay, second order unadam system. So like I mentioned this also, while calculating the high frequency region, the information of zeta is lost, hence we get huge error. Okay, just by seeing the Bode plot, we won't be able to tell about damping. Okay, that is one more thing. Okay, zeta is lost. Just by seeing the Bode plot, we won't be able to tell any information about damping, because like that is lost, because zeta tells the information about damping, and that is itself is lost. Okay, so yeah, this is the case. Now like we'll do one example with this, so we'll understand further. Now here, what about the critical damping? Like critical damping is very simple. Like obviously we won't get any resonant peak. Okay, obviously the resonant peak will be at the DC gain itself, but the Bode magnitude plot is very simple. It is like zeta equals to 1, hence real repeated rules, negative real repeated roots. Okay, negative real repeated roots. So that is fine. This is not okay. And this is minus 40 dB per ticket. This is 0 dB per ticket. Okay, so now like if you want to put the value, like if zeta is 1, then what does my T of j omega become? It is simply k omega n square divided by let me write in terms of s itself first. K omega n square s square plus 2 zeta omega n s, 2 omega n s, zeta is 1, plus omega n square. So now if you divide it, what will this become? So this will become k T of j omega equals to minus omega by omega n square plus 2 j omega by omega n plus 1. Or what you can do is like directly write here, because this is s plus omega n square, so you don't need to do this. Like you can write directly here that this is k omega n square by s plus omega n whole square. So obviously I have two repeated poles at omega n. Directly I can see two repeated poles at omega n. Pretty simple, right? Or like, let's convert this into general time constant format. J omega by plus 1. Okay, this also you can convert. Okay, here I can see two repeated poles at omega n. So no information is lost over here. No information is lost over here. Okay, so this is about my critical damping. Now, is there error here? Is there error? There is error here. What is the error? The error is simple. The error due to this corner frequency itself. Like the actual plot, what will be? So there will be 6 dB of error here, because not due to zeta, but due to the corner frequency itself. Due to the corner frequency itself. So do also take that in note, that there will be obviously error here due to the corner frequency. Okay, the simple error that we calculated. Okay, previously. So it was simply minus 3 into n. So n is like what is the number of corner frequencies present over here? 2. So minus 6 dB will be the error. Okay. So yeah, that is one thing I wanted to mention. So like, these are real negative real repeated poles, and these are complex conjugate poles. Okay, complex conjugate poles. Now, like, what about this is the critical damp, what about my overdamp systems? So overdamped is simple only. Here my zeta is greater than 0, greater than 1. So it is negative unequal real roots. So it's very simple. Very simple. This is the general case that we are used to doing. So this case is basically simple. Here my Bode plot can be written like this: k omega n square into s tau 1 plus 1. This is the first example that I took in the Bode plots, I think, into s tau 2 plus 1. Okay, so yeah, like obviously here let's assume that my tau 1 is greater than tau 2. Okay, so this is my corner frequency 1 by tau 1, and this is the corner frequency 1 by tau 2. So this is 20 log k. Okay, and here like this is minus 20 dB per decade. This is 0 dB per decade, and this is minus 40 dB per decade. Okay, so here that is the thing, basically, like here negative unequal real root, so that's why. So yeah, this is it for the Bode plots of second order system. So I will leave you with one question. Okay, and in the next session, this is a gate question, so try to solve this. Like this is also like for that simple second order based question only. So try to solve this with whatever we learned till now. Okay, and I'll see you in the next lecture. We'll solve this question and more questions, and through that we'll end our lecture, and then we'll start our new chapter, that is the controllers and compensators. So yeah, thank you for watching, and I will see you in the next lecture.